Today I'm going to be looking at a simulator that I created that simulates an ideal gas in 2 dimensions. Before we get started, let us look at some of the prerequisites for understanding this type of simulation. An ideal gas is a gas in which all molecular collisions are completely elastic. The definition of elastic collision states that the collision must preserve momentum and kinetic energy. Here we have the mathematical definition of the inelastic collisions. As usual, the values m1 and m2 are the mass of the particles. The vectors v1 and v2 are the initial velocities of two particles, and the vectors u1 and u2 are the final velocities of two particles after the collision has occurred. In 2 and 3 dimensions, angular momentum must also be preserved, but because the particles are often incredibly small, the angular momentum is assumed to be negligible. In our simulation, we can also assume that the masses of the two particles are the same, so we divide out the mass from both equations to get what you see here. Now we could try to solve this set of equations on our own, but if we use the Pythagorean theorem, we can get a solution while using a little algebra. If we assume that one of the masses is stationary, we can see that a solution to this equation happens when the final velocities are equal to the components of the initial velocity, which are normal and tangential to the contact surface. Now, converting this into formulas we can use in our simulation is sort of tricky, but it's much easier than straight up solving the original equation set. Let us get the final velocity of the stationary mass first. Getting the magnitude of the components of the velocity normal to the contact surface is fairly easy. We can call the normal vector equal to I hat, and the component of the velocity normal to the contact surface will just be v dot I hat. Calculating I hat is also fairly easy, as it's just the vector difference between the two positions divided by the magnitude of this difference. To get the actual vector velocity, we simply multiply our magnitude by I hat to get what you see here. Now, to generalize this answer, we simply have to shift our reference frame so that the object we are interested in has an initial velocity equal to 0. This simply means the final velocity is just the initial velocity minus the velocity we just calculated, v dot I hat all multiplied by I hat. To get the final velocity of the first mass, we simply compute the same calculation, but in a reference frame so that mass is stationary. This finally gets us to an answer that Wikipedia lists as the final velocities in an elastic collision. Now that we have gone into the prerequisites and have solved for elastic collisions, we can now get into the code. I started by creating my window in OpenGL with C++. I then created my circle by using a triangle fan. Once I had my circle, I created the shaders and I had a transformation uniform to be able to translate the circle around. I then created arrays for the position and velocity properties for each particle. I also created a mechanic to ensure that each particle stays inside the view frame by making each of the particles bounce off the walls with the opposite velocity. Before I implemented the elastic collisions, though, I created a graph library for reasons I will show later. I first created a function to draw a curve in a smaller part of the window. Then I created a function to implement a histogram. I then finally implemented the elastic collisions. I then used the histogram function made earlier to draw a frequency distribution of the velocities. This is what the final program looks like. I have roughly 1,000 particles, which all initially start at random velocities. Looking at the histogram in the bottom right corner, we can see that it approaches the Maxwell-Boltzmann frequency distribution. This distribution describes the probability of finding a certain particle at a specific velocity. That is all for today. Bye.